Okay, this is PreCalculus A Portfolio Unit 6. The worksheet that you need to download and complete is called the cleverly concealed conics portfolio. So conic sections are a particular set or class of functions, not even functions actually, equations that are all the result of slicing or dicing a cone, actually a pair of cones, one opening to the bottom, one opening to the top. And so they include the best known are circle, ellipse, parabola, and hyperbola, though they do include point, because a point is just a circle reduced to a radius of 0, and line, in fact, because a line is also a special case of a hyperbola, just with, yeah, but anyway. So let's take a look at the worksheet. I'm just going to kind of read through it and talk through some of the steps. Okay. You are asked to find examples in the real world of the conic sections. So examples of a circle. You can find all kinds. I would like to, use screen capture. You can Google search. You can screen capture with things like a car wheel, for example. Really good example. Okay. And let's see, an ellipse. Examples of ellipses. An ellipse is an oblong shape that has two focal points. One example I think of is I forget the name of the building, but the Mormon Tabernacle Choir sings in it. I don't think it's the actual tabernacle, but it's an elliptical shape, which is kind of interesting. It's actually an ellipsoid. Having trouble thinking of other examples of an ellipse in real life, but feel free to look around and see if you can find something. Let's see, there is an ellipse, there's a hyperbola. The best example of a hyperbola is the shadow cast by a lampshade. Okay? When you've got a lamp, it casts a shadow on the wall, kind of like this. It straightens out the further it goes out. And it does the same on the bottom as well. And a true hyperbola is double-sided. So a lamp is a good example. You may find some other examples. Okay. For a parabola, those actually exist quite a few places. There's parabolic reflector dishes, satellite dishes. Behind the headlight of your car is a parabolic reflector. Okay, and especially when you put the high beams on, any rays leaving the focal point will exit parallel. So a mirror reflector on a flashlight probably is a good example of a parabola in real life. So circle, ellipse, hyperbola, parabola. We're not going to deal with point and line. But I'm going to leave it up to you to find good examples and pictures. You can use the snip tool, copy and paste into a Word document. You can sketch them. Okay, where we're going here is this. Choose one of your conic examples to study in greater detail. Okay, I'm gonna put my foot down and say, do not pick a circle. Okay, the circle is trivial. It is boring. Because they have you double or half the distance between the focus and the vertex. A circle has no vertex, or you might say it has an infinite number of vertices. Okay, because a circle is kind of a special form of an ellipse in which both foci come together in the same point. Okay, So it's trivial, it's ridiculous to talk about doubling or halving focus to vertex distance in a circle. So choose an ellipse, choose a hyperbola, choose a parabola. Okay. Just for the fun of it, I'm going to choose an ellipse. So if possible, use a photo of the structure or item, otherwise draw a detailed sketch. Measure and label key dimensions of the shape in order to duplicate them to a scale graph. So I'm going to use Desmos. We're going to have a little bit of fun. So I'm going to pause this video here while I find a picture. All right, I've done a little bit of searching and I found a nice picture of a tennis racket. Actually, I think it's a badminton racket. And it'll serve as an ellipse here. So we're interested in fitting this to an equation. So I've saved the file, and what I'm going to do, I use the snip tool here. What I'm going to do is I'm going to open Desmos. So desmos.com/calculator. Click plus and click image. Okay, and it allows me to select an image. I've saved the image here. So there's my tennis racket. So we're going to try to fit an ellipse to this. So I'm going to just take a guess as to what I think the ellipse is right now. Remember the formula for an ellipse is x squared divided by the axis to the left and right squared. It seems to be about 2 to the right, left and right. So 2 squared. Okay. Plus y squared, all divided by in the vertical. Now it goes from 4 to about -3, so it seems to have a vertical of about 7, so 3.5 for a major axis. So I'm going to try 3, so it's a little less than 3.5, so 3.4 squared. Okay, and I'm going to say equals 1. We're just going to get a picture of it right now. And that's pretty darn good, actually. And we can fiddle with this a little bit. It's got a vertical shift on it, so I'm going to translate vertically by putting parentheses around the y. Okay, and I'm going to go minus 0.5, 0.6, 0.7. That's pretty good. And let's shrink the vertical to 3.3, increase the horizontal to 2.1. There we go. And that's a pretty good fit. I could sit here fiddling with it all day long. But that's the idea. All right. So we've got now a conic section that fits the picture of the tennis racket. Okay, so let's go back to the worksheet here. Okay. And all right. So if possible, use a photo of the structure or item. We did that. Draw a detailed sketch. Measure and label the key dimensions of the shape in order to duplicate. Draw the underlining conic section on a coordinate grid. Identify the coordinates of appropriate key parts. So we want to identify the coordinates of the focus, the coordinates of the major vertices, etc. Now I'm going to, for the purpose of this, I'm going to simplify this quite a bit. I'm going to take away the vertical shift. Okay. I'm going to simplify this to 3 squared. And I'm going to simplify this to 2 squared. And we're just going to do a little bit of math surrounding this particular ellipse. Okay. And I'm going to get rid of the picture for now. So that's the basic form of the ellipse. We could be more detailed if we wanted, but I'm not going to here. Okay. All right, so let's identify some of the major components here. So I'm going to grab a screen capture here and paste. Okay, there we go. All right. So some of the major items here, we have vertices. at -2, 0, and 2, 0. We have vertices at, and that's for the minor axis. The major axis, the major vertices are 0, 3, and 0, -3. Okay, and we need to find where the focus is. If you recall the way focus works here, okay, I'm just going to approximate the focus here for now. All right, and we examine this right triangle. Okay, this dimension here is the y dimension that I have labeled in my formula b. Okay, and this is the x dimension that I've labeled a. Okay, and the whole b actually happens to be the hypotenuse of the right triangle. So c, the distance from the center to the vertex, is given by this. So a squared plus b plus c squared equals b squared is true, right? Or more specifically here, b is 3, a is 2, so 3 squared here, 2 squared here, okay? So we get 4 plus c squared equals 9. C squared is 5, and c is the square root of 5. Square root of 5. So our foci are at square root of 5, or 0 square root of 5, and 0 negative square root of 5. Okay. All right. So those are the important places. Now, it asks us to either half or double the distance between focus and directrix. Okay. And so if we were to double, let's double the distance between focus and directrix while keeping everything else the same. So while keeping everything else the same, we're going to double this. That means this right here is the distance between focus and directrix, and that is 3 minus root 5. So we're going to just double that amount, right? We're going to double that amount and add another 3 minus root 5. Okay? So we're going to move the vertex out here, if that makes sense. Okay? Keeping everything else the same, which is also going to move this out. Okay? So that means, let me switch colors here. That means B, the new B, call it B prime, is going to be 3 plus what we added to it, 3 minus root 5. Okay? Or simplified 6 minus root 5. That's going to be B. The new A is still 2. Okay? And so my equation becomes, oh, and I need to, that's B and that's A. Yeah. Yep, that's right. So my equation becomes x squared over 2 squared equals y, not equals, plus y squared over 6 minus root 5, 6 minus root 5 squared. Okay, equals 1. And let's take a look at that in Desmos and see what that looks like. Okay, we're going to leave the original on there. So x squared over 2 squared plus y squared over, and I'm just going to put 6 minus square root 5 squared equals 1. Okay, and so just as we demonstrated earlier, the parabola is, or the ellipse is longer right? It's made it longer and skinnier. Okay. So double or half the distance from foci to focus to the vertex or vertices or vertex, and determine the new key points on the graph. Calculate what happens to the equation. Compare the new graph to the original graph. Write a paragraph explaining what would happen if our original example were changed in that way. So I'll leave the writing up to you. But you can see obviously that it's longer, but not any less wide, because we just changed the distance between the focus and the directrix, or the focus, not directrix, focus and vertex. Anyway, so hopefully that helps.